All right, those of you who are self-isolating, I hope you are all fit and well, and hope that you are just self-isolating as a precaution and that you are not poorly at all in any way, shape, or form. Anyway, I realised that actually there are 3 lessons coming up this week, and it's all going to be about trees. So actually, I'm just going to record as much of this as possible for you, what we're going to cover in the next 3 hours, and then you can work at it at your own pace. And I think that's probably the easiest way to do it. And what I'll do is I'll break up where I would say the lesson would have started and stopped, so you can then balance your time. Okay, so without any further ado, let's crack on. So I'm going to do a quick recap because I always do that at the start of lessons. So we're looking at the tree data structure. So this is going to be part of a family of data structures such as stacks and queues, and we are going to be looking at others such as lists and hash tables and graphs. Okay, so the tree data structure is made up of nodes. So each of these individual items on the screen is a node. Okay, so each node contains a value. Okay, so the node I've just circled is a B node. Okay, it has a value of B, and it also has children. Okay, in this case it has 2 children. The tree you can see on the screen at the moment is a generic tree because you can have between 0 or n children. Trees must not have cycles, so there should be no way that I can go from A to D to G and then over to C and back to A. Okay, so I shouldn't be able to create a loop like this. Apologies, it's quite hard to write with a laptop with a screen up, so apologies for that. Anyway, so you can't get cycles in a tree. So if a tree has a cycle, there's no longer a tree, we actually call it a graph. Some terminology, the root of the tree is called the root, it's the top of the tree, so we always start a traversal, any algorithm with a tree at the root. So we always start right here. Then each node will have a parent. Okay, so the parent of B is A, the parent of E is B, and we have children. The children are the nodes going down the tree. So the children of node B is going to be E and F. If a node has no children at all, we call it a leaf. Those terminology we'll use throughout the rest of the sessions. So to summarize, a tree contains multiple nodes to connect together with edges or branches. Okay, we tend to use the word branch when we talk about trees. However, you might see on the internet it called edges as well. It's the same thing, no difference. Has no loops, as I've already said. Key terms are the root is the first node of the tree, children are the nodes underneath a node that it's attached to, a leaf has no children, and finally, a subtree is just a small part of a tree. So we can code this using object-oriented programming. Do not worry too much about class tree. In all honesty, the thing I want you to focus in on is the class node. That becomes really, really important. Now, because we have 2 bits of information, we have the value itself, so the value it's going to be storing, that's the number or letter or word or whatever we put into the circle or the square, whatever we're using to represent it. And then we have the children. This is going to be an array. Because we can have 0 to n, we don't know how many of those will be in there. Therefore, we need a big data structure. If I'm truly being honest, it's not really an array. We tend to use a list for this because obviously it's dynamic. We can add to it, we can remove to it. But for now, we'll just call it an array. So if you remember, we did this coding task in lesson already, so you guys have already cracked on with this. So here we've got a class diagram. Okay, I'm going to be using that quite a lot, and you'll see that a lot in the exam questions. Class diagrams are really straightforward. You have got the name of the class, we have the attributes here, and those are the kind of things that describe each object, and then you've got the methods of things it can do. Okay, now when we are creating an object, okay, we need to make sure we have a variable to store it in. Okay, that's just we kind of call it the name of the object, but it's just a variable name. We obviously have assignment because you always use assignment when you're giving a value to a variable. And then finally we have the new keyword, which basically in pseudocode means create me new object please, and then we have the name of the class. Now when we create an object, we use the constructor of that class. Okay, and in this case the constructor is taking a value, the value that's going to go into the thing, and then we pass that through when we actually create it. So the root node has a number 5, and you'll probably notice here that we also have the value at 5 there. So that's a bit of summary for you guys. Then we start looking at traversals. Now breadth first traversal is dead easy. You start at the top, okay, you can imagine this layer 1, layer 2 and layer 3, and we simply, starting at the top, we'll work our way across each time. It's known as breadth first because breadth, you can think of the breadth of something going along as a kind of like a horizontal line. So we call it breadth first. The other type of algorithm we look at is obviously depth first, which is going up and down. So the breadth first algorithm, it's really easy to do in paper as a human because we literally just read it going across, dead easy. For the computer to do it, it's slightly more complex. We need another data structure to support us, and we need to have a queue. So the basic algorithm is this. We'll add the root node to the queue. We then remove from the queue. We add the children of the node we just removed to the queue, do something with the value, and then repeat all this until the queue is empty. So traversing a tree can be done either depth first or breadth first. We've looked at breadth first only so far in this video, but we have done both already. Breadth first traversal will visit each node on the level before moving on to the next, and it uses the queue. The queue data structures, please make sure you remember that because it's a classic question example we'll ask, and it's a classic thing to forget because we don't tend to do much with it in class and lessons, and the questions won't come up very often, but when they do, you don't want to be thrown by it. Cool stuff. Okay, and here's the code for it. You don't have to memorize this code. Be really clear on that. You don't have to memorize it, but you must be able to read it. Okay, so do take a moment to read through this. This is the English version. That one you should remember. Okay, so you can actually do it and explain it and talk about it. And this is the coding version of it if you were to code this in a language. I like this slide because what it does is it shows each element of the wordy algorithm, the English algorithm, the one that's easy to read, and shows where the code comes in. So as you can see, we have add a node to the queue. Well, I create a queue and I add the node to the queue, and that links to that one. And you can see each section of code are broken up into parts and shown what part it is. Okay, that helps reading it. This technique is brilliant for memorizing code and memorizing it from first principles. So rather than memorizing code, we memorize the algorithm, but remember what code each element does, and that helps us actually write it. I'll come on to how to memorize algorithms in a future lesson when we start covering the ones you do have to remember. Okay. Whew, a lot of information here, I'm sorry. So there are 3 types of trees you need to be aware of, and we have already covered this. The standard tree, which has more than 2 children in each node, or could have, should I say. Binary tree has a maximum level of 2, binary meaning 2. And binary search trees where we have an additional constraint of saying that every node on the left must be smaller than the parent, and every node on the right must be bigger. So, as I said before, for binary search trees, each node can only have a maximum of 2 children, and we call these left and right. Rather than having an array, we just simply have 2 extra variables called left and right, and that's it. The value of the left node will always be less than the parent, and the value on the right is always bigger. If we have 2 nodes which have the same value, then as long as we are consistent, it doesn't actually matter if we go left or right. Okay, so that will be up to you when you implement the algorithm. So again, we did this in lesson time. The node for binary search tree, you have left node and right node rather than having an array, as we said before. This time we include a parent. Now the parent for now, we're going to do nothing with it. This really kicks in when we start to look at removing elements from a tree, because it becomes really useful for that. And there are some other algorithms which we don't actually touch on that actually will benefit from knowing the parent. It just means we can step up in a tree a lot easier. So we don't need a list anymore, and null just means an empty branch. Okay, it's equivalent in Python to none. Okay, with a capital N. Right, here's the binary search tree. So again, we've done this in lesson time already. So the nodes on the left, you can see always less than, and then the nodes on the right going this way always greater than. Okay, that is always fixed. So if I was going to add another number, for example, let's say I was going to add, I don't know, 28 to this. Okay, well, 28 is greater than 16, so I'm going to go this way. It's bigger than 25, so I'm going to go this way. But it's smaller than 29, so it goes this way. So we'll go to the left of 29. Brilliant. So to summarize that, binary trees are trees where the node has a maximum of 2 children. Binary search trees have an additional condition that a node on the left will always be smaller. Binary search trees and binary trees are different, and you must know the difference between those two. Adding to binary search trees, use the basic rules that if the value of the node is less, then we put it onto the left node, and if the value is bigger, we put it on the right. Now, this is a good time to pause the video, check over your notes, to make sure you understand all of that, because the next stages don't make sense otherwise. Binary search trees are one of their favorites, guys, okay? So absolutely make sure you are absolutely confident before you press play again on this video. So pause now, check your notes, please, and then continue the video. So we've almost caught up with where we were, so a bit more catch up, guys. Inorder is where we will go through and basically in a binary search tree print the numbers out in order. This is obviously really, really useful. So for example, if I was using this data structure to display or store a database, for example, and trees are using databases behind the scenes, that's, you don't need to know that, but that is true. We can then print things out in order by simply doing a traversal. Okay, so in order we use a recursive function. Okay, notice we have the name of the function in order here, and then we have in order here and in order here. This recursive function is a bit different to the ones we are used to because there is no return. However, remember very, very clearly, when a function ends, we always return. So here I've got the value of 16, so I call in order on 16. Okay, so the first thing we do is check to see whether it's null or not. Well, it's not, it's 16, it's not null. So we then call in order on the left node. So we end up with a stack being produced, the function stack. Okay, all recursion use the function stack to actually manage what's going on. So we've already called it with 16. We then call in order again with 5. Now, when we call the function, we always start at the start again. So I'm going back to here. I check if it's null. It's not. Well, then I am going to call in order again on the left node. Well, I'm at 5 at the moment. Going left will give me 2. So I call the function on 2. Then I go back to the start again. I run start the code again because I'm now doing it with a value of 2. It's not null still. Then we call in order on the left node. Okay. Now I'm going to call in order. This time it has the value of null. Why does it have the value null? But look, there's nothing on the left hand side. Remember, when we create a node in a binary search tree, we set the left and right nodes to be null, and then we change those to real values should it have actual children. So the left of node 2 is null. Therefore, when we come back and run this line of code here, it is null. So, oh, excuse me, I didn't burp then. I absolutely did not burp. That is not something that happened in the video. Okay, absolutely not. So you are imagining it. So if you come in back to lesson and you have a bit of a giggle with me, then I know you actually watched this video. So let's actually do that as a test. So I actually am testing you on that one. Anyway, so we always have to have a bit of laugh, don't we, guys? So we are calling this thing, it's got a value of null, so it's going to skip over the if statement completely, and it's going to go straight back here. Now the function is now end, so we are returning. So we are returning, and we go back to where we will call the function. So we're now at 2. Now we call the function here, if you remember. So we're now going to run the next line of code, which is print, which is why the first value we get is 2. We then call in order again, but this time on the right node. So we're going to add null again to the stack, because if we go to the right of that, you can see there's nothing there again, so we call it null. So nothing's going to happen. So this function ends. So we then pop that, and we go back to 5, and just continue that onwards. So that's what's happening behind the scenes. But hopefully, as we did in lesson time, you can see why we got this order. So pre-order is exactly the same. I'm not going to go over exactly how it works with the recursion again because it's exactly the same, there's no difference. The key difference is we always print first, okay? So we call it on 16, we print 16 immediately, okay? We always go left first, we call it on the 5, so we print the 5 out, okay? Then we go left, print it on the 2, then we come back, we can't go right, so we come back, we go right here, so we print out the 25. And then we keep going through that pattern to get those list numbers. And the key thing to remember, pre-order, pre meaning at the start. Okay, so we do something at the start. So we always get the root at the start here. Post-order, exactly the same. This time the print is at the end of the function. So we go left, then right, then we print. Okay, the root, as you can see, is at the end because that's what will always happen with post-order because it happens at the end, the last thing it does. So really quickly, okay, so we'll always go left first, then we go left again, we try and go left, can't, try and go right, we can't, then we print. Okay, we then come back, we try and go right, we can't, print the 5 out, we go back, we try and go right, we can, we try and go left, we can, we try and go left, we can, 17 is the next one we print out, and then that pattern continues. So this is where we picked off now. So I think it's a good time to pause just to make sure you're happy with that. We're now going to look at depth first on generic tree. Now, this ironically is exactly the same code, but it doesn't look the same, does it? Okay, but let's actually really think about it. So we're currently looking at pre-order. Now remember, pre-start. Yeah, so prefix is at the start of a word. Pre always means at the start. So you probably notice that I've got this weird thing. I've said perform operation. Now, I'm introducing a second idea here, okay, which is although we've been printing each time, maybe I don't want to print. Maybe I'm doing a search. So depth first traversals are sometimes used for searching. Sometimes they're used for other things as well. So I'm using perform operation to basically mean the thing you want to do on each node. Okay, whether you're searching for it, whether you're trying to find a path through the tree, or whatever happens to be, if you're just printing, it doesn't matter what it is, that's what perform operation is. If you want to make this a bit easier on you, that you can just think of that as a print statement, if the idea of another operation starts to confuse you. Okay, but for now, let's just pretend it's print. Now, remember on a generic tree, we can have no children, or we can have 20. So we've got an array now, we have a list, don't we? So we can't just simply go left and right. Okay, so we now have a loop. This is the slight difference. So you can see how I'm using a counter-controlled loop, a for loop. Okay, so I'm using the pseudocode version of this. It's not the Python version, although you could easily use the Python version in this as well. We just like nice and straightforward. And then for each child, we call pre-order generic again on that child. Okay, notice I'm using the array notation. So remember, children are an array, and I am starting at 0, the 0 index, that's the first item in the array, going to the length of it, -1, because remember, the last index is the length -1, isn't it? So that's why we've got that. And then I'm just simply calling it like that. Okay, so node dot children n. So it works exactly the same way as binary trees in all honesty. Okay, the key difference is we now have a loop. So that's the difference. And here are the two algorithms for post order and in order. Notice the loop stays the same. Okay, that loop does not change. Now for post order, remember we do it last, the operation last. So we have the loop first, and then we do the operation. In order is slightly weirder, because what we do is we call in order on each child, and then we do the value. So it's slightly different, but the key thing here is the perform operation is inside the loop. For in order, for post order, it's at the after the loop, and pre-order is at the start. This is a brilliant place to stop, ladies and gentlemen. So pause time, make notes on that. Get that code into your notes. If you wish to, absolutely, you can replace perform operation with print if that just makes more sense to you. If you get the idea that we might do other things and perform other operations such as searching, then leave it as perform operation. Just put in the notes, something like this. So this could be any operation, and you can maybe clarify that a bit more with, it could be a print, it could be search or whatever. Okay, so brilliant point to pause. The other thing I would suggest you do is you've already got a generic tree. If you have access to that file, if you happen to have it, then have a go at coding it. If you don't worry about it. If you want to, you could try and recode a tree and again do that, because I know, so Hope, you probably will want to do that because you know you're into your coding, and to be fair, I think it's the best way to learn it. But I know some of you may not be able to write it from first principles. Again, that's fine. It's not a big deal. Maybe when you do come back, you can have a go at it then. Okay, guys. So pause time. Okay, summary. Depth first traversals come in 3 flavors. We have in order, pre-order, and post-order. The key differences is when we perform the operation or print a value out. So in order, it happens in between, pre-order happens at the start, and post-order happens at the end. So we also have a termination clause, and that is this if statement here. And the termination clause will stop recursion from occurring. Our generic trees is very, very similar. The key difference is we are going to be using a loop instead of no loop, I guess, because we have lots of children. But where we perform the operation, where we do our prints, is exactly the same. So pre, start, post, at the end, in the middle of the loop. So we've already had a look at how we add nodes to a binary search tree, which is essentially where we'll start at the top of the node and we'll kind of work our way down until we find a place where there is no leaf, where there's no chart, and then we put it in. Now, removing from a binary search tree is slightly more difficult. Now, for this one, the algorithm behind it is easy enough to understand. Okay, there's a slight complexity to it, but it's not too bad. The coding for it, however, is much more challenging. So you will not be asked to code removal from a tree, other than like the most simple cases. You will not be expected to memorize the entirety code for it, because quite frankly, I don't think many computer scientists can just do it off the top of my head. They'll probably have to have a little think about it. So with that in mind, we're going to look at the removal. And as it turns out, removal from a tree comes in 3 cases. We have a case where we're removing a leaf. Now remember, a leaf is a node with no children. So in this case, I have colored it in green. So we have this leaf. Now that is the simplest way of doing it, the simplest one. Because if you think about it logically, well, if I want to remove 27, well, bang, I just get rid of that link, wouldn't I? So I can set 29's left to null, bang, I've done. So nice and easy. We then have the situation where we have 1 child. Now that situation is, again, fairly straightforward, because what I'll do, and this is where the parent comes in, the parent of 5 is 16. And what I want to do is, I want to remove 5, so I get its parents, and I make its left node equal its child. So you see 5's child is 2, so I make 16's child to be 2 as well. So essentially, bypassing 5. Okay, that's how we remove it for a when there's 1 child. Multiple children, however, there is a more complex algorithm we have to implement. It's straightforward enough once you get your hang around it, but it's obviously the most complex case. So we have 3 cases that we have to handle. So removable link, we simply just remove the parents link. So 27 will go to its parent 29, okay, and then we will set its child to be null. And that effectively takes it out of the tree, and then I can just delete the node. When you have 1 child, you simply link the child to the node's parent, okay? So as I said before, we have 5, we look at its parent, which is 16, we look at its child, which is 2, and then we make 16's child to be 2. Okay, the same would happen for the right node as well. So if it happened to be 1 child, but this time on the right, we did exactly the same thing. Okay, we look at its child, and then we link that back up. If we have multiple children, however, we have to use something called the in-order successor. Now, in-order successors is a very, very, very posh way of saying the next biggest number. okay, the next biggest number in order successor. This only works for binary search trees, by the way, because we want to maintain the order, don't we? So if I remove a node, I want to make sure it's always still having the rules of left is smaller, right is bigger. Okay, so we have to maintain the integrity of the binary search tree. So in order successor, how do we find it? So imagine I want to remove a node. So let's say I want to remove 25. Now, 25, we need to find the next biggest number. Now, how do we do that? Well, the next biggest number has to be to the right, doesn't it? Okay, because of binary search trees, the right is always greater than, isn't it? Okay, so we go right once. Now, 29 is where we are at. However, that's not the next biggest number. So what I need to do is I need to find the smallest number. This is where it gets a bit weird. The smallest number to the right of the node I'm removing, the in order successor. Okay. The way to just think about it, we go right once, go right once, and then 2. We go left as far as we can. So if we follow that logic, okay, we go right once to 29, then we go left once because we can't go further left, and 27s are in order successor. If you look logically at the tree, 27 is the next biggest number, isn't it? Okay, so that's how we find it. Let's look at 16. How do I find the in order successor? So I go right once, and then I find the next smallest number. Well, it goes left as far as I can. I go left, I can go left again, and I found 17. 17 is the next biggest number. Okay, we can do that on any node. Let's say you want to go 20, so I go right once, I go left as far as I can. Well, 23 is, there's no more left, so 23 will be it. Okay, so it finds the next one. Go right once, left as far as we can, the in order successor. So we can think of it as the leftmost child of the right subtree. Okay, so what do I mean by that? So again, let's look at 25. The subtree, we go, we get the leftmost child of the right subtree. The right subtree is anything connected to the right of this. Okay, so anything connected to the right of it is now the subtree. So we have a subtree there, and we find the leftmost node. If I want to, let's just going to get rid of that. If we want to find the 16, what we do is we find the right subtree, which is all of this, and then we go left as far as we can, which is 17. Okay, that's another way of thinking about it. So the full algorithm, when we've got multiple children, is we find the next biggest number, the in order successor, we swap it with the node we're trying to remove, and then we remove that node as if it was a leaf, because when we find the in order successor, it's guaranteed to be a leaf. Okay, always will be. So let's see this in action. So let's say I want to remove 16 from this tree. So as you can see, we've got multiple children, so we have to use the algorithm. So I look at the right subtree, so I go right once. Then I find the leftmost node. Okay, so I go left as far as I can, which is 17. So what happens is I swap 16 to be 17, and I make that 16. Okay, I then can remove 16 completely. Okay, it's gone, it's now destroyed, and then I'm done. So if you look at the tree very carefully, okay, well, we've got 17 at the root now, so 5 is smaller, 2 is smaller, brilliant, we haven't broken it yet. 25 is bigger, 20 is bigger, 23 is bigger, 29 is bigger, 27 is bigger, we're not broken anything. So the binary search tree has remained correct, it's retained its integrity, therefore the algorithm has worked. Now, there's a reason why you don't want to memorize this code, because here is the code for it. Removal is incredibly complicated code, okay? It's to the point where I wouldn't necessarily expect you to fully follow this. I know some of you who may be a little bit shaky with recursion and a little bit shaky with OO coding. This code, you might look at it and go, that's really hard. that's fine. Okay, I'm not expecting you to be able to read this level of code. Okay, nor would I expect you to be able to code it. Those of you who are a little bit more savvy with your recursion and your coding, you may wish to have a read through this code and actually try and understand it and see how you get on with that. So, removing from binary search trees has 3 cases. Okay, case 1, the node's a leaf, bang, we'll just get rid of it. Easy peasy. 2, it has a single child, so we link its parent to its child. And third one, the node has 2 children, we find it's in the order successor, we swap with the node I want to remove, and then finally I remove it as if it was a leaf. Okay, so those are the 3 cases you need to do. Okay, the reality of exam questions on this will be you have to do it, you don't necessarily have to explain the algorithm of how it's done. Okay, and if you were asked to explain the algorithm, it would be in words and not in code. So this is a really good time to pause the video and actually go over how to remove from a tree, because obviously that will help you massively. Do make sure you include the 3 scenarios. You don't need to include the code, guys. And in lesson, I will be kind of showing people the code in the binary search tree. I've coded it already, so not, again, you don't have to code it, just to see how it works and how it's been implemented. But again, you don't have to memorize it. So, the last thing we need to look at is how do we do this without object-oriented programming. Now, the coding for this without OO is slightly trickier because we're now going to have to use arrays to implement this through arrays. So we're going to have a lot more array indexing to deal with, which I personally think makes it a little bit more complicated. However, the algorithms don't change, how we do it doesn't change. It's how we store the tree has changed. Okay. Now, exam questions on this are actually much more simple than you think they would be. They are going to show you the array implementation, so a tree, using the array implementation, and you've just got to fill out the blanks. Basically, that's the kind of questions that come out. So we will look at that style of question as we go on as well. Okay. So here we go. This is the array version. Now, when students first see this, they go, what on earth is going on here? However, this is not as difficult as it looks. So we've got a number of things. Now, we first of all have the index. Now, the index is the array index, okay? Like you would have in any array, you start at 0, okay? So if I have an array in this example of 10 values, okay, the first value is going to have an index of 0 and so forth, okay? So that's all this is. Okay, notice this is a table, so hopefully you think, aha, that's a 2D array, isn't it, Ms. Hamlet? And you'd be right, it is a 2D array. Well done for spotting that. Then we have our 3 items. Now remember, when we have a node, there's 3 pieces of information we stored, wasn't there? We had the left node, the right node, and the actual item, the value that we are storing. Okay, that's what's represented here. Okay, so we essentially have a 2D array. So if we look at the item here, imagine this is called tree as an array. Okay, this item here is going to be tree. Well, it's at index 0, and we're looking at 0, 1, and 2. So it's going to be 2. Okay, so get the value out for the first item in the tree, the root of the tree is going to be that. Then we look at these numbers. These numbers are also indexes. Well, we now have the E in my tree. Well, what's on the left? It's 2 at the left. Well, what's that position 2? Or index 2, sorry. The value of C. So to the left is going to be C. What's at the right of it? Index 1. What's at index 1? It's G. Pause the video now, have a go at doing that, and then I want you to have a go also at how can we add B to this. So if I created another item here, B, how do we do that? How would we update this tree? Okay, how would we update the array? Have a go at that, and we'll go for the answer in a moment. So here we go. Now, this was a genuine exam question, by the way. I changed the values slightly, but the question itself, the structure of it is exactly the same. The table is coded into a TD array called tree. So, first of all, notice that we have B added in position 5. Now, this is a binary search tree. Okay, so let's draw the tree out as we had it. So we had E at the roots. Okay, then on the left of that we had C, and on the right of that we had G. Okay, then if we look at G, it's got -1 and -1. That means nothing. -1 is our null in this example. And at 2 we had 3 and 4. Well, position 3 was A, so to the left we had A. Okay, and then to the right we had 4, which is D. Now, where would B go? This is a binary search tree, so B is less than E, B is less than C, B is greater than A, isn't it? So it would go here. So we need to link it up to the right of A. Well, looking at A, there is the right there. So I make it the index of that. So it's no longer -1, we change to 5. So that is what we do. You'll also notice, the eagle-eyed amongst you, that the 3 has also changed. So what is 3? Well, 3 is basically saying the next 3 index in my tree. Okay, that way we know where to put the next node into the tree. Okay, so that's what we did here. So it was 5, we're now pointing to 6, because that's the next empty value in my array. So the marks you would get would be for essentially changing the index there, for putting the value in. Make sure you put -1 here. Okay, absolutely, a load of people get that bit wrong. They put 0 or they put something else random. You must put -1. -1 is null in this implementation. So -1 equals null. Okay, do put that in your notes, that's really important. So now, this table is coded into a 2D array called tree. Here's a bit of a challenge for you, so pause the video time again. Write a function that will return true or false if an item is found. So the function find is going to take a 2D array in, like this. So you might want to code this as a 2D array in Python straight away. Then you call the function and say find, I don't know, G, and it's going to say yes, I found it, or no, I didn't. If I did a search for, I don't know, F, well, there's no F in there, so it would return false. So you've got to code that. Okay, have a think about this. This isn't as straightforward as you probably think it might be. Okay, what I would say you're going to do is you're effectively going to implement binary search. Okay, so this is essentially doing binary search. Have a think about it, have a go at it, pause the video. I'm going to go over the answer in a second. So here's the answer. Now, the algorithm itself is very small. You can see there's not much code here. It doesn't look pretty though, does it? Okay, and the reason it doesn't look pretty is because we have a lot of array indexes to deal with. Okay, now you probably can see why I prefer to teach OO coding first rather than second. Okay, so let's have a look at this. We have our function find. Well, we have our parameters. I've already given you that, job done. Okay, now we always start at the root of a tree, and in an array indexed a tree, the root is always at position 0, index 0. Okay, so we always know that. So index 0 is where we're starting. So then we have the loop. While start does not equal -1. So what's that mean? What it means is, if I get to a point where I'm looking at a leaf, so I'm trying to look at maybe a smaller value or bigger value, and there's nothing there because it's a child, it's a leaf, then I want to stop and I'll return false. Okay. Otherwise, I want to check to see whether it is equal to the item. Okay. So if the item we're looking at is equal to the thing I'm trying to look for, then I want to stop the loop and say, brilliant, excellent, I found it. There is more than one way to implement this, by the way, but this is the way I've chosen. So, how on earth does tree start to equal the item I'm looking for. So remember, I might be searching for the value, I don't know, of G. So how does that actually work? Well, start is which row in the table I'm looking at. So remember, it was listed out like this. We might have index 0, we have left, right, and value. Okay, the left might be pointing to another index, the right might be pointing to another index. This might be E, for example. Well, start is 0, so we're looking at the root node. This, think of it like a mini array, and I'm comparing the value out. Well, it's remember 0, 1, and 2, so it's the value. So this 2 is representing the value. Okay, so that is essentially, when we say 2, we really mean the value of the item. Then we've got the binary search part. Okay, so remember, if the value is smaller, well, I want to go left, don't I? If the value is bigger, I want to go to right. So let's have a look at that. I'm looking at if the value is smaller. I've just noticed there's a typo there. That should be 2. Never mind. If the value, remember 2 is value always, is smaller than the item, then I want to go left. Well, I need to change the start index. Remember, this is always going to be an index now. It's not going to be a node because that's object orientated. It's an index into my 2D array. Which row am I interested in? Okay, and that's going to be left. Okay, so in this example here, I want to make the index equal to 2. Okay, so notice I say start equals. So I'm changing this variable, and I'm changing it to be whatever's at index 0 on that one. Remember, that is my left. If I was going to right, I'm going to change it to 1, which would be this value. Okay, so if it's bigger, I'm going to the right, so I need to get index 1 for my mini array. If it's left, I'm going to get index 0. A lot of people sometimes think the index is 0, that's 1, that's 2, and that's 3. That's not true because the index, you don't store the index, do you? It's just the index. We show it on the table because otherwise it just becomes really hard to read it as a human. But in the computer, we don't store it explicitly. It's just the index, the way we get into it. Hopefully that made sense. So that keeps going until we get to a null, okay, -1. As soon as that point, if there is -1, that means we didn't find it, we return false. If it's not -1, we return true. Now, it won't be -1 if we find it because that will trigger this one, won't it? Because it is equal to the item. Both of these must be true in order for the loop to run. Therefore, the loop will end early. And the start variable won't be -1. It will have a number, and that number will be where it's found. If I wanted to return its position rather than true or false, well, I could ditch that if statement completely and just go return start. Because if it's -1, it wasn't found. If it's any other number, then that will be the index of where it was found. Okay. We can do this recursively as well. Okay, so exact same code, but we've got two end clauses. Remember, like the while loop, we had two conditions in the while loop. We had the two ands. So if those were not true, then we keep going. Otherwise, we stop. Okay, same here. So if the current equals -1, okay, so that will be the current index we're looking at. Then we return false. We didn't find it. If the value is equal to item, then we return true. Okay, because that's the other end clause, isn't it? We either find it or we don't. We stop if we find it, we stop if we don't find it. Okay, those are the two things that stop my recursion. Otherwise, what I do is I have the same if statement. Notice the if statement's not changed, but this time I recursively call find. I keep the same item because that's not changing. The tree itself is not changing. Okay. Now I could use the tree as a global variable. In this example, I'm passing it through. It doesn't matter for this kind of code which way you do it. I prefer to pass things through just because I do. Then notice this is the same as we had before. So remember, we're making start equal tree current 0, the left node. Okay, this time we're just passing it through as the parameter. Okay, and the same thing happens here. So if it's bigger, we just do that. So that's the recursive version of this, okay? If they asked you to code this, which they could, so this is one of the ones they could ask you to do, they can do, and also they can do this in OO coding or array-based coding, which this is why this one's a little bit more tricky. Then recursive or iterative is fine, whichever one you prefer to learn, okay? They are not likely to tell you to write both of them. They could be cruel and give you one, say write the other, but just bear that one in mind. I've already talked to you guys how to convert recursive functions into iterative and vice versa, so hopefully you will remember that and be able to turn between the two. So what I'd like you to do, and this is a little bit more tricky, is write in order, post order and pre-order for the table implementation, the array implementation of a binary search tree, okay? I'd like you to stick with recursive because that's how I've taught you how to do it already. And the recursive functions are just being tweaked, okay? So rather than going node.left, it will be the name of your tree, the index you're looking at, and 0 for left, or 1 for right, okay? So, key learning points, ladies and gentlemen. So we're almost done. You need to learn the ideas behind binary search trees, okay? That is fundamental. The way they can be implemented may change in the exam questions, okay? They may show you the OO version of it. They may talk about array versions of it. So you don't know which one they're going to ask about, so you need to know both. The two implementation methods have been shown, but they are subtly different in the exam. Don't memorize the code for it, okay? You need to be able to read it and create it from first principles, not memorize. So don't try and memorize that code because it's hard to memorize abstract code. I mean, genuinely really hard to memorize abstract code unless you've got like Sheldon Cooper kind of memories. It's just hard. So you need to know the algorithm of what needs to happen, and then be able to piece together the code based on that. Okay. So that's what I mean by first principles. So notes task. Create a new page called Array Implemented BST. Show the example in this PowerPoint. Explain how it works. Explain how to add and remove from it using algorithms we already explained. Show the code for traversal and searching, and explain how it differs from OO coding. So you might need to make sure you have coded the traversals just to practice. Obviously, if you get stuck in that, email me and I'll go through it with you guys when you get back. I'm aware it's slightly trickier. I haven't put the answer to this PowerPoint because I want you to try. So my suggestion is try it, send me your code that you tried, and I can tell you where you went wrong basically. The big tip I'll give you on that one though is code it exactly the same as you would do for the OO version of it, but change the parameters. Okay, so change when you call in order, for example, as the recursive call, change what goes inside the parameters inside those brackets. If you do that, you won't go too far wrong. Okay.